talked about thermal circulations at low levels of the atmosphere and over small regions and sea breezes. But we can also talk about thermal circulations and how the global circulation works. So a scientist by the name of Hadley had an idea that the atmosphere would work in a thermally driven circulation for the entire planet and came up with the one-cell model. Basically thinking the equator gets really hot, the poles get very cold, so that hot air is going to rise, cold air is going to sink. As the sinking air hits the lowest part of hits the surface, it's going to spread out and move towards the equator. As that rising air hits the upper part of the troposphere and spreads out, it's going to move towards the poles, and you'll get a global circulation. Unfortunately, this didn't line up perfectly with the observations, and there are a few good reasons why. Specifically, this single cell model of the planet makes three key assumptions that aren't how the planet actually works. It assumes the whole planet is covered with water, not the case, that there are no seasons, certainly not the case, and the Earth doesn't rotate, so pressure gradient force is the only game in town, rather than Coriolis force forcing things to turn to the right or left, depending on the hemisphere you're in. Because of these three assumptions, this thermally direct circulation, due to the equator heating up, only makes it to about 30 degrees north and 30 degrees south. So we needed a better model of the global circulation. So they got rid of some of these assumptions. They let the Earth rotate, and that gave us the three-cell model, which I'm about to show you, and which is a decidedly more accurate model. So again, they still call this thermally direct circulation, and note the direction this moves. The warm air rises, moves towards the poles, sinks, and then the surface air moves back towards the equator. You have this thermally direct circulation. They refer to it as the Hadley cell because it lines up. And again, think of how the air moves here. Part of the reason it only makes it to 30 degrees north, the main reason, is because of that addition of rotation. The Coriolis force sort of puts an upper bound on how far this air can move before it starts turning entirely parallel to the direction the planet is moving. Similarly, they looked at the polar regions and saw a thermally direct circulation as well. So again, you have cold air sinking at the poles and then spreading out, moving towards the equator, but it only makes it to around 60 degrees, again, because of that Coriolis force. But once it hits 60 degrees, it starts rising up and getting warm, the warm air rises and completes that thermally direct circulation. It's moving in the same direction. So surface air is moving towards the equator, upper level air is moving towards the pole, and you've got cold air sinking, warm air rising. This leaves the gap right in between the two regions, 60 degrees and 30 degrees, that we call the Ferrel cell, named after the scientist who largely discovered it. And note, it moves in an opposite direction. The surface winds are moving towards the pole, the upper level winds are moving towards the equator, and you've got sinking air on the equatorward side and rising air on the poleward side. This is a thermally indirect circulation. It is the result of these two circulations. Basically, some of the air that rises in the polar cell at around 60 degrees doesn't make it all back north. It starts headed south. Similarly, at 30 degrees, some of this sinking air that hits the ground right around 30 degrees, it's not just all going back towards the equator. Some of it spreads out north. So you end up with this thermally indirect circulation forced by two thermally direct circulations surrounding it. Oh, this lines up with what we see wind do throughout the planet. In the tropics, you've got the trade winds moving. So instead of moving directly north and south like the single cell model indicates, you've got them moving from west to east in both hemispheres. In our region of the world, instead of winds moving north and south, north to south again, you get the west to east moving winds. So similar to what we see in our area, what direction storms generally move, they move from west to east for the most part. We'll talk about next week how storms move differently, and a little bit more about this junction between the polar regions and our regions.